Good evening, everyone. I'm Ellen Rathje. I really appreciate you all spending this afternoon and evening with us to hear about the New Zealand earthquakes. Brendan did a great job introducing the two events, and what I'll be doing in the next 15 to 20 minutes is to talk a little bit about the reconnaissance that was performed after these two events, and really how we've started to bring new technologies into play where maybe 10 years ago they were very uncommon to use these type of technologies, but really they are becoming the norm for our reconnaissance going forward. I always forget the acknowledgements, so I'm putting them up first. And so the stuff I'm going to present today represents the accumulation of effort from a lot of people. We had a large team down in Kaikoura after the event, people from GNS, which is the New Zealand's equivalent of the USGS, many people on our GEER team, the USGS as well. So I want to acknowledge all of them. And I'll show you some stuff that we've been doing in satellite remote sensing, and I just want to acknowledge the students as well as the colleagues in New Zealand and the US who have been working on that with me. So I think when I look at the GEER experience over the last 15 years when we've been in existence, there's really in the last, say, 5 to 6 years what I like to call a renaissance and reconnaissance. And we're moving really from qualitative observations where we go out and we take pictures and make important observations, but they're still qualitative. And now we're starting to really make quantitative measurements of what has occurred. And when we look at the ability to make those quantitative measurements, we're taking advantage of various technologies, and the ones I'll talk about today are satellite imagery. Probably you've all at least played around on Google Earth or Google Maps, so you all know what we can see from the sky. But I'll talk a little bit more about how we're using them, again, not just to look at damage, but to measure and document. And then, of course, there's LiDAR, and we're also more frequently using UAVs. So when you look at these three different technologies, they play different roles in the reconnaissance. If you look first at satellite imagery, you really can get the big picture. You can look at regional scale assessments. So I just show you here the shake maps for the two events that Brendan introduced so well, the Christchurch and Kaikoura events. You know, if you look at the areas affected, we're talking about hundreds to thousands of square miles. And to try and get a rapid assessment of what has occurred is quite difficult. Yet the satellite imagery can play a role in documenting these earthquake effects at a regional scale. And in particular, when you look at geotechnical effects, such as liquefaction or landslides, they're particularly well suited for using satellite imagery to identify those effects. So I'll talk a little bit about satellite imagery with respect to both liquefaction and landslides. But also our reconnaissance teams now are almost always bringing in people who do LiDAR. And the LiDAR allows us to look, when we're looking at a site scale, so a single site, being able to develop detailed 3D models, and probably many of you are starting to use LiDAR perhaps in your own work here in New York. But in case you're not familiar, LiDAR takes advantage of lasers, and you shoot the laser at the ground, measure the travel time to get the distance, and knowing the location of where you sent that laser, you can then develop a 3D digital elevation model. We can put the LiDAR on a plane, we can put it on a tripod, but in the end we can get a really nice 3D point cloud. Here's an example from the Chile earthquake in 2010 of an embankment failure, and you can see very clearly the failure on the edge. And now we're not just taking pictures of this, we can actually start making some real measurements. Another technology that's really just starting, I think, to make its way into our reconnaissance is the ability to develop 3D models using simply a large collection of photographs. And this, back in the day was called digital photogrammetry, now often called structure from motion. The key here is if you take photographs of the same area from different points of location, we can put them in a computer algorithm. The computer can identify common points in all the images, calculate where you took each image from, and with all that information can actually develop 3D point clouds. So much cheaper than trying to have a laser, putting on an aircraft, etc. So you can take these pictures standing on the ground, or more commonly now we're using UAVs. So we can put these cameras on UAVs, take these pictures, be able to take the pictures from over a much broader area than you could on the ground, and then you can develop a 3D model. And here's just an example from a paper I took in geomorphology, where from about 3,000 photographs, which is quite a lot, you can see this rock outcrop, which is about 40 meters or so wide. You can see the detail that is put together in the 3D model. So I'm going to talk a little bit again about how we're using these different technologies for the different earthquakes, the Christchurch and the Kaikoura events. So Brendan already showed you the widespread liquefaction that occurred during the Christchurch earthquake, and that's indicated here again by the warm red colors, where is the most severe liquefaction. And a lot of this initial mapping at this broader scale was actually done by looking at air photos and satellite imagery. And you can simply look, here's just an example of one area along the Avon River pre-earthquake. We can see all the homes, we can see the roads, we can see the bridge looking pretty, looking undamaged before the event. And then after the earthquake, we can see lots of ejecta. You can see some cracks. You can see some damage on the bridge as well. So here you can see relatively quickly, we can identify damage and start identifying where people need to go in terms of doing their reconnaissance. And this makes us much more prepared when we go into the field. We're not going out into the field asking people, what did you see? Where should we go? We know already where we want to go when we are looking at reconnaissance. But more recently, we've taken satellite imagery, I think, to the next level and what we can do with it. And we've been able to measure displacements, horizontal displacements, using the pre- and post-event satellite imagery. So here, if we have a satellite image of the Christchurch area as shown here, one before and one after the earthquake, if we align them very well with each other, then we can identify where segments of each the image have moved in between the two acquisitions. And we did this analysis for the Christchurch event. And here, looking in that small study area, these are the displacement amplitudes along the Avon River. So you can see, for instance, in this north-south stretch, we've got amplitudes that tend to be in the 2 to 2.5 meter range right along the river. We can see them grading back to, say, less than a half a meter further away. Of course, so you would see that this is indicating movement towards the river, lateral spreading due to the liquefaction. Of course, when we first got this result, we said we have to look at some hard field data. Do we trust these displacements? And so the first thing we did is we looked at where people had mapped cracks. And you see that the cracks map generally along the largest displacements that we've observed. Now, of course, cracks mean you're only measuring displacements that manifest themselves on cracks, no ductile displacement. Satellite imagery shows you a little bit more detail of that ductile displacement, but they're very consistent with one another. And now you can get a displacement map of essentially the entire city. And we've also looked at some very detailed comparisons from Transects, for instance, where people have measured displacement cracks as a function of distance from the river. And so you can see that the displacement trends and the profiles from the imagery and the ground surveys match quite well. And so it's very encouraging to see how this type of data can now be used to better understand liquefaction, and in particular, lateral spreading and the movements caused by liquefaction. And when you start having large-scale maps where you have displacements across an entire region, it really opens up what we can start looking at. So here on the left, you see displacements that we've measured. The hot spots are, again, the largest displacements. And on the right, you see a digital elevation model, which came from LiDAR. And you can start seeing, well, how topography perhaps influenced these displacements by looking at, how far inland things extended, how does that compare to the topography, the geology, et cetera. So it really opens up a lot of research avenues for helping us understand liquefaction and lateral spreading. So let me move on to the Kaikoura earthquake, which happened, as you heard, just a few months ago. Landslides, we knew from the outset, from the initial reports, were the major concern. But it was unknown really how extensive the landsliding was, or let's say how far it extended inland, how far it extended up and down the coast. They very quickly got into the air in helicopters and were taking lots of pictures. But still, it was still a snapshot. They knew it was quite bad, a lot of landslides, but the extent was still a little unknown. We came in and started to look at what we could see from the satellite imagery. First of all, landslides are perfectly suited for identifying on satellite imagery, because typically you strip the vegetation, and so what was green before is now brown, and that's typically a landslide. In this event, Landsat, which is a satellite that is run by NASA, actually captured imagery the day after the earthquake. We had that imagery within another day or so. But the problem always with optical imagery is cloud cover. So although the Landsat image the scene was probably this big, the blue area is the only area that was cloud-free. So it was the only area we could identify landslides. The other difficulty with Landsat is resolution. The fact is, each pixel is 15 meters by 15 meters, and so you can't see smaller landslides, and the detail is somewhat limited. But within just a few days, high-resolution imagery came in. The USGS has agreements with the commercial companies that collect these data, and they made it available to our GEER team. And so and the pink area here represents all the different scenes that we analyzed at that high resolution. And we were able to develop our first landslide inventory within about 5 days after the event, and shared that with the GNS and the folks in country there. And it really helped guide us in our GEER reconnaissance as we went out into the field. So let's take a look at Clarence. So this Clarence is, the Clarence River comes into the ocean here a little bit further to the north. The epicenter of the earthquake is down here, and then Wellington would be off the north edge of the island there. So in terms of identifying landslides, which we did manually, which may sound quite difficult, we tried to do some semi-automated techniques, but in the end, it was quicker to just have my graduate student click and find all those landslides, and he did a marvelous job. And so each of these red areas represent landslides, polygons that were indicated by the stripped vegetation. You can look at the geology right next door and start to see some interesting trends. So first of all, you see a higher density of landslides in this area, which is the gray area here is represented by a gray wacky sandstone, which is pretty pervasive on the North Island. So you can see there are localized areas of landslides in the gray wacky. There's some really interesting things going on down here, larger landslides, and you can see that's an area where there's some complex geology going on. We've got mudstone to the east, a little bit of limestone, and then we're on to the gray wacky again. And so that ended up being quite an interesting area where we started to look at. But let me show you a little bit about the different character of the different types of landslides. If we look in the gray wacky, a lot of areas, they were relatively shallow volume. So you can see, similar to what Brendan showed along the coastal road. This may be a shallow landslide, but it's certainly enough to make that road to be unusable for up to a year. Further inland in the gray wacky, you'd see similar shallow landslides. But there were not only shallow landslides in the gray wacky. Some of the largest landslides happened in the gray wacky, and these were deeper seated landslides that caused very critical landslide dams that they were very concerned about. So you can see all this material coming down, blocking the river, and a very substantial landslide dam created. There were dozens of landslide dams created. There was concern if they were breached, what would happen downstream. And so GNS's major concern when we were there was to document and characterize these, both how big they are, and then trying to model what would happen if they breached, and how far would the water reach downstream, and what communities would be impacted. And they used LiDAR to help in that effort. For me, some of the most interesting landslide I have ever seen are shown right here. Some of these deep-seated landslides that happened at the interface between the mudstone and the limestone. So you can see here on the Leda River, which is in the south near Waiu, this entire area used to be up there. So this is about a scale of 1 kilometer long. This landslide, when I first saw that picture before I went, I thought this was the White Cliffs of Dover. I couldn't understand what this looked like before. It was, all this material was all there. So these are, again, landslides that are on the kilometer scale. As Brendan showed, the fault rupture was quite complex. That was our word of the week, complex, on the things that we saw. I like to say that this looks like just a glass shattered. The fault rupture went one way, turned left, then turned right. It really is fascinating. But if you look at those two areas that I just showed you, Clarence up along the coast and then the Leda River further down the south, they both occurred in areas where the fault rupture went through the landslide. So this idea of how the fault rupture interacted with the landslides is something that we'll be studying for quite some time. So let me just quickly go through the Clarence area because it's really interesting to see what was happening here. So again, here's the coastline. These are the several landslides that have occurred in relatively close proximity to one another. That was called Limestone Hill. That's because there's on the back side is where the limestone is. There's a limestone quarry in the back. But this side is mudstone. This was, we called the cowslip line landslide. If you saw the news, the cows that were stuck on the little grassy promenade, that's where that happened. Although the farmer begged us not to call it cowslip anymore because he was getting hounded on social media by animal rights groups for not taking good care of his cows. But in the end, it's really the best name because everyone knows about the cows. So that's the cowslip landslide. Again, we've got this limestone. You can really clearly see this limestone here, but note this brown and gray. That's the mudstone. So we're seeing here's the interaction. The fault is right there. If we go further to the south, we see some shallow slides. And in fact, if we start looking at the geology, some of it starts to look very interesting. Again, the mudstone to the east, limestone hill, cowslip right along the interface. This is the fault. And then the superficial slides were completely and solely in the limestone. So a completely different style of landsliding. That's the Papatia fault. Parts of the Papatia fault had 10 meters of displacement. Yet this fault was mapped as inactive because there was no evidence that it was active, at least in the Quaternary. So that was very critical. So if we look, I got these from one of our colleagues that looked at the fault rupture. So here's the fault rupture going right through the landslide. And as we go, so this is on the north side of cowslip. And then there's a little tree there. If we look through that tree, so we see the fault rupture continuing on. Here's Limestone Hill. Another small landslide in the middle, which in any other earthquake would have been a big landslide, but not in this one. And then we can see it continuing right across the river. So very interesting in terms of what was the impact of the fault rupture being through the landslide on this movement? Would the ground shaking have caused it solely? Was it simply the fact that we had limestone on top of mudstone, that interface at the fault? How did those all play together? And that's something, again, we'll be studying, I think, for a while. But as I mentioned, we brought in a lot of technology for this event. We brought in drones to be able to develop 3D models of some of these landslides. We had LiDAR. This is GNS's LiDAR. We also, from Oregon State, brought in some LiDAR. So the LiDAR was used on the landslide dams. It was used on some of these landslides. Also, some of these landslides were so big, using the terrestrial LiDAR has really been difficult, and they're planning on flying LiDAR over these areas in the near future. But just to give you an idea of what you can get out of this, so this is if you simply go into Google Earth and try and zoom in, this is what the cowslip landslide looked like before. I think it's a great place for your cows to graze. But that's what it looked like after. And this is a 3D model that was developed by John Manaukis, who was our drone pilot and our geomatics expert. And so this is a 3D model that we then have rendered in Google Earth. But now you can start developing 2D cross-section, 3D cross-sections to start better understanding the geometry. Finally, just to bring things back to infrastructure, I do want to talk about how we use these technologies to look at the infrastructure response. And here's just an example of a train culvert, which the coastal road went over. We drove it every day. We noticed there was, some movement and ground movement at the surface. So when we went down and looked at walked through the culvert, looked a little distorted. And then, instead of spending the day taking measurements, which in the past what we would have done, a couple days later, Mike Olson came in with his LiDAR and scanned not only the culvert itself, but also the surface. And as you notice, this is kind of a slope down over the culvert up to the road. And then you could start getting now a 3D model of the culvert and start really characterizing the change in shape, the movements at the surface, and seeing how this really moderate amount of movement due to the slope could cause quite a bit of ovaling to the culvert. So in summary, you've seen what we can do today now with satellite imagery in terms of rapidly evaluating regional damage. We can now even measure horizontal displacements, and I think that's really going to revolutionize our understanding of liquefaction effects. And then we're really starting to bring in these 3D terrain models, whether we develop them through LiDAR or structure from motion, so that we can better understand the geometries and use those as inputs, say, to numerical analyses we may do of these failures. And I would be remiss if I didn't mention the fact that all of this data that is being collected is now going to be shared. We really haven't had a mechanism to publish data from these reconnaissance efforts. And so the data that you're seeing here from the LiDAR, from the satellite imagery, we are in the process of archiving them and publishing them for future research via DesignSafe, which I didn't pay Sissy to mention it, but she did. And so I would be remiss if I didn't mention it as well. And so again, this is a cyber infrastructure funded by the NSF for natural hazards engineering. And there's published data that you may use. There are tools that you can do data analysis on that data, and as well as a reconnaissance portal that we're in the midst of developing. And so check it out, and you will soon find the data from the reconnaissance there. Thank you.